Welcome. In today's video, we will develop the equation for the volume of a sphere using techniques of calculus by spherical coordinates. Here is a sphere. Let me draw another perspective here so you can appreciate more that in fact what we're going to consider today is indeed a sphere. We have rectangular coordinates as I've outlined here, the x coordinate, y, and z. Our sphere has a radius of capital R, and to approach this problem using spherical coordinates, let's remind ourselves that a point within this sphere, let's suppose it's this point right here. This point, of course, in rectangular coordinates would have the order triple x, y, z. In spherical coordinates, we can locate this point by a line going from the origin out to the point itself, and that would be the radial line. That radial line is going to be located at some azimuthal angle measured from the z-axis here. So let me denote that azimuthal angle here as phi. Let me write that over here. So phi is the azimuthal angle measured to radial line from positive z-axis. Moreover, we could say that if I were to project this point, which is within this sphere, down into the xy plane, it may intersect the xy plane down here, and that is going to have the following x and y coordinates. So I'm going to take this point here and I'm going to draw a line parallel to the y-axis from it, and then from this point I'm going to draw a line parallel to the z-axis until it intersects the y-axis. And so this distance here I would say is the y-coordinate of the point as it's projected down into the xy plane. So this would be the y-coordinate, as I just said. This will then be your x-coordinate. And if this line has a radial distance, let me call it r, then if I were to project r down into the xy plane, it's going to have that length, and I can call this, of course, if this is phi, then by alternate angles, this is also phi. And so that means that this length here is going to be r sine of phi, and that means that that was gotten by the azimuthal angle, but spherical coordinates have an ordered triple of r, phi, and then this sweeping angle which sweeps into the xy plane. Let me call that theta. Okay, so then I could say that this length here, the r sine phi, which is the projection of our radial line out to the point, is going to have a y dimension, as I've denoted here, of r sine phi sine of theta, which is gotten by this, if you consider that this is a right triangle lying in that xy plane. Likewise, we would say that this is r sine of phi times the cosine of theta. And of course, the point itself is lying at some vertical height, z, which is r times the cos of phi. All right, so having done that, now let's move over and remind ourselves what a volume element would look like in spherical coordinates. So let me redraw the x, y, and z axes. Here's your x, y, and z, and we want to focus our attention momentarily on a differential volume element lying in this x, y, and z coordinate system. So once again, we have some radial length r. That radial length, so supposing that this is the radial length r, from the z-axis we could denote this as our azimuthal angle phi, and that would mean that this little angle in here is d phi, and I'm going to now formulate a small differential volume such that this length of the volume element is the radial differential length dr. We now know how to compute the arc length from a previous video, and the arc length having r and this interior angle of d phi means that this arc length here is going to be r d phi. And also, we will remember that we've dealt now with the azimuthal case and also the radial case, but we also have a sweeping angle down into the xy plane, and we will account for that next by drawing this sweeping angle of the differential volume here. Such that this distance here is going to be the radial length r times the sine of phi Okay, so that's the radial length here times the sine of this azimuthal angle. And I'm going to draw a line parallel to the x-axis from this point and show that, in fact, this angle here is the sweeping angle theta out to that position, such that this angle here is d theta. That means that if I have this length here as r sine of phi, and the interior angle here as d theta, that means that this arc length here is going to be the length r sine theta, or I'm sorry, r sine phi times d theta. Great. So now we have all the pieces to the puzzle for the volume element. We've got the height of dr, and we've got these two arc lengths. One is r d phi, and the other is r sine phi d theta. And so I can go ahead and state that the differential volume dV is equal to the height dr, which is this dimension here, times this base, this side of the base of that differential volume, r d phi, times the one that was swept inside of the xy plane, which is r sine of phi d theta, and that's this dimension here. So putting it in the order of r, phi, and theta, I could write that d volume is equal to r squared, that's from this r and that r being multiplied together, times sine of phi due to that term, times dr d phi d theta. Now that I have the differential volume in terms of spherical parameters r, phi, and theta, I am in a position to be able now to go ahead and integrate both sides of this. But before doing that, we want to be sure we understand the limits of integration. So let's just talk about that real quick. Notice that, starting with r, that r ranges from the origin here, 0, to the radial length of the sphere itself, which we were told in the beginning that the radial length of the sphere is r. So let's go ahead and denote that first, that r ranges between 0 to r. The azimuthal angle phi goes from 0 at the positive x-axis, and it goes down all the way to pi at the minus side of the z-axis. So phi is from 0 to pi radians. And lastly, this angle that sweeps within the xy plane goes from 0 at the positive x-axis, and it does a full circle all the way back around. So theta ranges between 0 and 2 pi. Now we can integrate both sides of this equation here. Let me try that again. All right. So integrating both sides of this equation, we get the volume when I integrate on the left, and that's what we're looking for. On the right, we're going to have a triple integral. So we have, let me write these spread out a little bit. I'm going to have the sine squared phi term relative to the phi integral. And then in the innermost integral, I'm going to have the r squared. So first of all, the sine squared, the sine, that shouldn't be squared, that should just be sine. The sine phi came from this term here. And that's relative to, it's nested within the phi integral. Nested within the innermost integral, which is relative to r, is the r squared term, which is this one. And we have here the radial differential term dr. And then we're going to perform this innermost one with respect to r first. And then after we do that, we will do our integral with respect to phi. And lastly, we will finish up with an integration relative to the sweeping xy plane angle theta. And now let me fill in what the limits of integration here are. So r runs between 0 and cap r. Phi runs between 0 and pi. And theta goes between 0 and 2 pi. So beginning with the first one then, we get, this is theta is 0 to 2 pi. And this is phi is 0 to pi. The integral of r squared dr is r cubed over 3, and just by inspection we can see that we've got a cap r that's going to be subbed in and a 0 at the bottom limit, so the only surviving term will be the cap r, so it's going to be a third that I'll bring out of here, r cubed. Now we have the sine of phi, which is this term that we have to integrate with respect to, and then we will finish up with the d theta. The integral of sine phi d phi is nothing other than minus cos of phi, so we get r cubed over 3 times the integral theta goes from 0 to 2 pi of minus cos of phi, as phi runs between 0 and pi. And then we will lastly do that last integral with respect to theta. Let's go ahead and put the limits of integration into here. So we get then r cubed over 3 times the integral theta goes from 0 to 2 pi, and we put the first limit of integration inside there. That would be minus cos of pi minus a minus cos of 0 d theta. Now cos of pi, let's just quickly remind ourselves what that would look like. So the graph of pi looks something like this, such that this is 2 pi and this is pi. That means that down here, when cos is pi, the value of cos of pi is minus 1. So we get here a minus from this term times a minus 1 for the cos of pi, minus that minus, and cos of 0 obviously is just 1. This is where the angle theta is 0. And this is the graph of cos of the angle. Let me be a little more precise. We were talking about phi. So let me call this phi and this phi. And so the cos of 0 is 1, so we get a minus times a minus 1. This is that minus. And that's a plus 1, and then this is also a plus 1. So all of this comes out to being 2. So let me bring that out. So I have 2r cubed over 3 times the integral going between theta is 0 to theta is 2 pi. And this is with respect to theta, of course. So that's an easy integral to perform. The integral of d theta is nothing other than theta, so we get 2r cubed over 3 times theta evaluated between theta ranging between 0 and 2 pi. And of course, by inspection, we can see that that's going to be 2 pi minus 0, which is 2 pi. So we get 2. So the volume, of course, this was all with respect to the integration to find the volume. So the volume is 2 pi times 2r cubed is 4 pi r cubed over 3. And that's the equation for the volume of a sphere. Equation for the volume of a solid sphere. I hope that helped, and we will see you at a future video once again.